is a matrix, we can expand this ideas.
in an and is a to the power iota ht divided by h bar. Uh, this so this is a and this quantity what you call it as uh, now create this unitary operator that is our e to the power iota ht into various segments. And once you diagonalize this, we can actually get the final state. So as I said, in quantum system, any kind of things I want to do, that I can actually uh, take it actually. So once I diagonalize this, solvable easily. When written here that when it and we get the corresponding unitary operators and we ended up getting the Qiskit. But so this there is nothing quantum computing here. There is nothing anything that is incorporated. Anything I have incorporated quantum computing I have incorporated. But what is the problem here is when it scales. When this Hamiltonian matrix scales, uh, so the dimension of the Hamiltonian matrix when it scales up, it becomes very hard to manually calculate by hand. So if a quantum computer can somehow solve it, or if a quantum computer can exactly help me to do it, that would be a really good thing, because there will be some uh, usefulness of in terms of advantage. We can show the usefulness of quantum computers. Now, as I said, the problem here is where it becomes hard is when the dimension of the Hilbert space increases. It blows up uh, so for n qubits, the total number of the possible states, as we all know, the 2 to the power n. And when we want to simulate this, both time and memory explode very quickly. So this is the problem we will have or will face when the dimension of the Hilbert space as well as the Hamiltonian matrix increases by a lot. So we need to find some other ways, or maybe some ways that a quantum computer can solve it. Now these are the traditional uh, numerical methods that can help us to utilize this whole operator, that is our e to the power iota ht, which may look a very simple, crisp term, but it is not so much simple. Why? Because I've just explained in the previous slides that it's an infinite series, and it's not a very straightforward and very simple way to write it down and to calculate this. Uh, so these are some of the traditional methods. One is the trotterization product formulas. One is linear combination of unitary, which is the sum of unitaries, and another one is the truncated Taylor series. So, but in my slide, in my presentation, I'll be mostly speaking about the product formula, focusing on Suzuki trotter decomposition. Now there is one more problem. So as I said, I wanted to solve this equation, right? Why? Because it will help me to get the evolved state over a certain amount of time of a quantum system. What it will do for me? It will help me to calculate or simulate molecules over a certain amount of time. I will be able to know how a molecule will behave after a certain amount of time. Uh, that this equation, if I somehow able to solve this equation, I'll be able to do that. Now I can do it by hand, but just I said, the problem arises when the dimension of the Hamiltonian matrix increases by large. So there is one more problem, as I was saying, that H is a matrix and H cannot be consist of a single term. It can consist of multiple terms. 1, 2, 3, 4, you name it, 10,000, 50. Classically, doing it by your hand, almost impossible. One more thing, I think because exponential of the algebra of basically exponential of any number. So nothing very complicated and nothing very, it's a very straightforward way to do it. But when it becomes a matrix, in quantum mechanics we call it as an operator, we cannot do it. Why? Because if A and B does not commute with each other, that means A comma B, AB minus BA not equals to 0, we cannot write this, because if we comes along the way. So if this term equals to 0, then we will be able to see equals to this. In most of the cases, it does not commutes with each other. So A and B does not equals to this, which may be a very of things, which does not intuitively follow the traditional algebraic methods. Yeah. So as I said, I can create a circuit of this by each card. So how I can create this circuit from scratch without knowing any quantum computing, only but just knowing mathematics. All right. So this is the main idea that so I'll divide this whole operator into chunks, and I'll create so many chunks that wonder how do I know that this will be exactly power of, let's say, this is a, that's why you call it as an approximation method. So the main idea of tautorization is to break this whole unit and say 10 seconds or 20 seconds. So I'm breaking that whole thing into small chunks. The whole unitary operator I'll be breaking into small chunks, and I'll be creating the molecular Hamiltonian kind it's very different that how we experience everything that is around you see around yourself. It's a 3D world. It has three dimension. But the challenging thing, you could have easily imagined that how whatever you see around yourself, this 3D world, how you can encode this into a quantum computer so that a quantum computer can understand your problem. So a quantum computer does not what is 3D space, what is 4D space, or what is 2D space. So we have to somehow encode this whole Hamiltonian form in such a way that a quantum computer can actually understand. So this is the standard mapping. There are also a lot of procedures and mappings that are already available, and that are already there. But this is kind of the standard way to do it. So first we have the molecular Hamiltonian form. So I think how many of you have heard? All right. So where you have the two terms. So Hamiltonian basically, if you have a system, if you have, let's say you have a system, Hamiltonian is that quantity. You have a box. Imagine you have a box. Okay, enclosed six, like the dicey box. And inside that, there is a particle. So Hamiltonian in physics, Hamiltonian is that quantity which will include all the information that is available in that box. Like if you consider that box as a system, although it might be very crude to sound that as a quantum system, but if you consider that a quantum system, so a Hamiltonian is that quantity that will tell you each and everything about that system. So that's known as the Hamiltonian quantity. It includes two things. One is the kinetic energy, and another one is the potential energy. So if you write down the, although it's a very don't get intimidated by all of this equation, since you are mostly beginner, so I would like to highlight the fact that just try to get the idea about what exactly am I doing. You may not necessarily understand what all the detailed mathematics, but the Hamiltonian of a molecule, like let's say I have a H2O molecule, H2O, or let's say I have a CH4, or let's say I have some more complicated molecule. So the Hamiltonian will look, if I try to write it, as I said, Hamiltonian includes all the information of a quantum of a system. So it generally kind of takes a form like this, right? A mathematical form where these are the nuclear repulsion terms, and these are the these are the electron repulsion term. These are the electron nuclear repulsion term. So all the information, it is encoded here. Now a quantum computer will not understand, or it does not have any capability to understand this, how it is. So it's our responsibility to make the quantum computer or quantum algorithm understand that how this molecular Hamiltonian uh, you can analyze. So to do that, we follow the standard procedure of from going from molecular Hamiltonian to second quantized form, which is this. Again, there's a lot of mathematics involved, but just get the flavor of it, that from how it is getting done. So where A dagger Q is a creation operator, and AP is the annihilation operator. Now, from the second quantized, which is the fermionic form of the Hamiltonian, we get to the qubit form. Now, this once we using mapping, we ended up getting the Hamiltonian operators equivalent form that a quantum computer can actually handle, which is nothing but in this form. So you see, I have applied some kind of the logic or some kind of way of thinking, so that my from this molecular Hamiltonian, I came to this qubit Hamiltonian without losing any information. So that is a very challenging thing. So once you have the qubit Hamiltonian, that means I have, let's say I have a H2O molecule. Now, if I do all of these operations and stuff, I'll ended up having a Hamiltonian that has all the information of that H2O molecule, such that a quantum computer can actually handle. Now, for example, I have tried to showcase here how a 3-qubit Hamiltonian will look like. So here, this is the Hamiltonian term. And Yeah, yeah. It's a very I is the identity operator and Z is the Z get basically. So what? All right. So as I said, my operator just to break this into multiple slice. Just so I have started off with my Hamiltonian of this. So just get the flavor of it. That I'm not formation of my H2 molecule into this Hamiltonian, but I have taken some example of it. Now both order one. Um, what exactly will I get is so as I said, now my unitary operator that yeah. So my why I think I already highlighted that fact, but my main motive was to create how to solve this equation using a quantum computer, and to do that, I needed some HT. Now, yeah, the e to the power iota HT. If I just replace this H into this, I'll be getting this for a Chausian time and a reasonable decomposition strategy. So I think these are the matrices. All of your all these gates, X, Y, Z, are nothing but these matrices. Similarly, Rx, Ry, Rz, that whatever you see in all Rx, Ry, Rz, if you just see the mathematics behind uh, how exactly the matrix of it looks like, so it exactly looks in this form. Okay. And if you just apply R pi by 2 or X pi or I pi by 2, so what I'll do is I'll X as Ry minus pi by 2 Z Ry plus pi by 2, and I can use this properties. And if I just replace this, I'll be creating those slices. So just with my unitary operator, this right, this was try to see how it actually is been created, how the circuit is actually been created. Then I can actually create the whole circuit of it, which is once you understand the one step, the first step, the remaining steps becomes very easy. So that is exactly how the circuit has been built. So we can write this x, y, z. So I have taken only a single term, and x, y, z can be written as ry minus pi by 2 tensor product rx pi by 2 and tensor product iota this way. So I can, if uh, one by one, you will end up having this. Now, once again, once I have this form, and if I now I think all of you have heard about some kind of a C naught gates. Yeah. So C naught gates, if I can write this as a combination of these C naught gates, right? So if you write qubit is 1 and the target qubit is 3, you can create, you can actually multiply these matrices and you can get exactly this form of the uh, ZZZ. Now adding just like I said, this is not a very straightforward way. Like this is not a very simple also. once the only way to realize this is once you do the mathematics by hand, then you'll be able to understand how it is exactly coming from this step to this step, right? So as I said, this whole unitary operator can be decomposed into some basis gates like this, and once I have that, I can move forward with the other terms as well. Yeah. So just like I've said, this will be the circuit for the first slice, right? So you will have the RY gate, RX gate, and corresponding C0 gates. Just like I've said, you can see here, the first I am applying the C0 gates, there will be some RY gate, then there will be C0 gates, C0 gates, and correspondingly, the reverse parity that I'm applying here, C0 2 to 3 and C0 1 to 3. And which, so I have just, you see, I have just derived this whole circuit from this, from an unitary operator just by following mathematics, right? So that's the beauty of attacking any problem by just doing maths and logical reasoning, which helped me actually to create this full circuit. So you can see here the XYZ and YYX, the first two terms becomes the circuit, equivalent circuit of this is because becomes like this, and the other two terms equivalent circuit becomes like this. Now this is a continuation. So this continues. Now don't think this two rows. So here is first row, here is second row. The second row will be coming here. So it is a continuation of it, right? So as I've taken the example of a 3-qubit system, so this will be a complete row. Now, if I break those slices into, let's say, k number of k slices, so this will, all the slices would look like. So here, this is the first slice, this is the second slice, this is the third slice. Now what is inside these slices? These circuits, these continuation circuits. So this will continue from here, this, and this will come into a single slice, right? So yeah, and in this way, in, remember my initial goal was to create the, calculate the final state using a quantum computer. So you see, I just created the equivalent quantum circuit of this operator, the unitary operator. So now I can implement this circuit into a quantum hardware and calculate the final state. Now, where exactly these kind of problems can be relevant? So I think some of you have already heard about some of the practical use cases of a quantum computer, such as till we achieve fault tolerant devices by 2029. Let's say IBM have promised that. Before that, all of your quantum problems, it's either a simulation problem or an optimization problem, right? Once we have that a certain kind of a fault tolerant devices, then only then we will, our QML algorithms, the quantum machine learning algorithms, can be useful and beneficial. Before that, all of our quantum machine learning, whatever quantum machine learning algorithms that are already available there is actually no advantage. So if you see, there is actually no quantum advantage there. It's fact. So before fault tolerance, all of our problems are basically either it's a simulation problem or an optimization problem. So all of our problems we try to somehow manage to direct into these two categories. So this, through this trotterization algorithm, you'll be able to visualize or able to imagine how this can be relevant, how much this can be relevant in terms of simulation problems. So this actually helped me, this algorithm will actually help me to understand how a quantum system will evolve or how a quantum system will behave after a certain amount of time, which your natural instinct, your hand, your eyes, your nose cannot detect, right? Because a quantum system, you don't, can't visualize like a normal system, right? It's a because of its scale, right? So as I said, the uh, so I have created the the equivalent quantum circuit of this whole unitary operator, right? So by creating these slices, and what is inside these slices? Inside these slices, there are the each of these uh, circuits, right? So now what about the circuit depth? Now we still talk about some 1, 2, 3 gates. Like in Bell state, we also do some, put some one gate, some other C0 gate, some 1, 2 gates, right? But here you see, it's not only 1, 2 gates. You can see for only one slice, how many gates are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. And 4 times 9 is how much? 36. And for, let's say, I am running it for 500 slices. So how many gates will be there? 500 times 36. So you can imagine how many gates will be there. So it's not a like one gate, two gate, three gate. We're just trying to analyze what is going on, understanding, or no, it's not like that. So we need to analyze how many gates we require or how many depth we have to go to create accurate simulation. So this is kind of an intuitive idea about how it relates to it. So how it once you have the circuit depth, and if you want to reach to a certain simulation accuracy, and how much circuit depth you have to go. So the more slices you go, the better accuracy you will achieve. So which simply suggests that depth is proportional to gate count. Yeah. So this was the kind of the whole workflow of this algorithm, that once you're given the Hamiltonian in the Pauli strings, you can do some Pauli decomposition and mapping, and then you create the trotterized equivalent quantum circuit of that unitary operator, and you run the quantum simulation, which you can run on the quantum hardware, and you finally do the measurement and do the observables and calculate the expectation value of the observables. And here each slice is one small step. If I repeat this for k times, I'll get the full evaluation. Now, what is the output of it? I can calculate the expectation value of those quantities, like any quantity, right? So now, how do I know? How do I know that whatever I have generated is correct or not? So you should have argued with me that, okay, I am saying that this is my circuit, that this is my circuit, and how am I claiming that this is correct? How do I know that, right? So how do I know that then? I have created a time evolution of 1D potential well. Have you heard about 1D potential well? Anyone? No one? One dimensional potential. It's a classic quantum mechanics problem. You have one guy. Okay. So none of us. Okay. All right. So 1D potential well problem is a classic David J. Griffiths problem. It's a very starting problem in quantum mechanics courses. Um, yeah. So in 1D potential well, if you see the time evolution of that 1D potential well and how the probability distribution moves over time, it exactly looks like this. Now, as I said, I have created the equivalent circuit of this time evolution operator, and if I incorporate that, I am getting in the exact same time evolution state. So that's how I get to know that whatever I have generated, whatever my circuit is, it's actually a correct one. It's actually giving me the right result. And that's exactly, I feel like, you do research. You do some validation, you create your stuff, and you do some validation, and you match with the existing results. If it matches, congratulations, your research work is well defined and it's moving forward. So in Quniverse, actually, I have implemented this algorithm myself. And this is the classic 4 steps that you need to perform to uh, uh, to to understand or to do or to implement this algorithm into the Quniverse. So first you select the algorithm from the algorithm plate, which is a Suzuki trotterized algorithm, and then you load graph. Now, what is the load graph? I'll just explain. But just before that, I'll just try to highlight that how many of you have heard about the quantity named fidelity? So yeah, so fidelity is a quantity which measures how much my quantum state is accurate. So if it is close to 1, that means my quantum state is accurate. If it is close to 0, that means whatever quantum state I do have, it's a very crude approximation. It's a very wrong approximation. So the better the fidelity, better our simulation. And what do you mean by better? Better is close to 1. So fidelity will always lie between 0 to 1. So this will be my, then I'll hit the load graph. And once I have the load graph, then I'll set some parameters. Based on my parameters, I'll able to see how my system is evolving with time. And then finally, I'll load it and run it, which will show me the evolved state, which the initial goal that that I have started off with, which is nothing but to solve this equation. All right. So I'll just quickly go into the universe to showcase actually how um, it can be done. All right. So just give me a time to log in. All right. So here, if you go into the algorithm palette, and if you go here in the next update, people who have already registered in this platform, in the next update, you will receive this algorithm. But I think for the free users, that algorithm is still not available. So if you hit the load circuit button, here is my Hamiltonian input that I have in the Pauli string. And this is my initial state. And for order one, and if I select, remember those slices that I have talked about, like 50 slices, 1000 slices, 2000 slices. The more I go, the better accuracy I'll receive. I'll reach. And for time, let's say how much? Let's say 5 seconds I want to simulate for. Now, if I hit the fidelity visualization, I'll have a fidelity visualization understanding about how the fidelity is behaving over a certain time and how it is behaving over the number of the steps. So the more number of steps I go, the closer fidelity goes to 1. So as I said, the more the fidelity close to 1, the better our simulation results are. So yeah, so this is as you can see with the 29 step, I'm reaching out to fidelity close to 1. So if I take 29 size slices, that is good enough for this kind of Hamiltonian to create the equivalent circuit. So once I have that fidelity visualization, based on that, I'll change my input. So I have given the 50 steps, which already includes these 29 steps. So I'll have not a lot of problem with that. So if I just hit the load button, you see, I will redirect to another page. And if I hit the run button, so my Quniverse will run this algorithm for me. And I'll have a unique job ID for this particular job description. And if I just click on it, I'll just refresh it. So it takes a bit of time. So it's still running actually. Yeah, it's done. So you see, this is the exact final state vector that I was supposed to get. And this is the final state vector that I have got using my algorithm. So if you just try to merge this thing together, and the fidelity I'm receiving is 0.99. Now, the probability distribution matches quite similar with the exact final state vector that I was supposed to receive with the trotterized simulation version. So that's exactly says that whatever simulation or whatever the circuit that I've run is actually a correct one. So now our team, CDAC, our team itself is working in this platform also to show the circuit. It's still not visible, the circuit. There is yeah, so there is some internal things that they are doing right now to showcase the circuits also, because because it's not very easy to showcase the circuit as well, because as I said, the length and the depth of the circuit is very large. So I just gave you just a number, right? 36 times 500. So those number of gates I'll have in my circuit. So you can imagine how long, how big, how large my circuit can become. So which is a very challenging thing to show that circuit here in a very a short space. So with this, I think I have covered the whole trotterization algorithm. So I know this can be a bit challenging to understand in the first place, but if you have this analogy of breaking every complex task into very small, step by step, doable way, you can actually attack any kind of problem. And that's exactly how I have done it. I have implemented this algorithm from scratch. Yes, so with this, I'd like to conclude my presentation, and I'd be open for any kind of questions you all of you have. No questions. Wow. You can ask, no problem, no matter how basic it is. No questions? Okay. Yeah. Done, I guess done.
Sir, can you explain the time evolution graph in details?
Yes, yes, huh?
Time evolution graph.
Time evaluation graph,
Graph.
of course. Of course. Well, yes. So this is the graph that I think you were specifically referring to. So once I have my Hamiltonian expression, let's say uh, I have it has to be in terms of Pauli gates x, y, z, I, uh, just 0.3 star y, 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 x. So for example, this is my Hamiltonian. This can be very large also. You can put whatever you want, just a very random way. Uh, and I'm choosing my initial state as 0, 0, 0, 0. So the number of the qubit that I'm choosing for the initial state as well as my Hamiltonian should be matching. Why? Because the number of the qubit of the system should be remain consistent throughout our uh, throughout whatever calculations we are doing. So if you choose the initial state of a 3 qubit system, it will throw you some error. So which will say invalid initial state, it's the syntax error. So which actually says that you have to put your initial state of a 4 qubit system. So here I can select the Suzuki Trotter order, and then the number of the slices that you want to reach. Let's say I want to reach 100 slices, and I want to simulate it for uh, 2 seconds. So if I do the fidelity visualization, so this graph actually speaks about fidelity visualization. Now, as I said, fidelity is a quantity that helps us to understand uh, how much our state is accurate, right? So if the fidelity always be lying between 0 and 1, so if it is close to 1, that means my state is correct, and if it is close to 0, that means my state is the whatever simulation I have done, it's not that correct. So you see, as I said, my Hamiltonian expression was very easy. If I incorporate, let's say, 10 seconds, so I'll get the fidelity visualization curve. So it will take a bit of time, I guess, because I have increased the time by a lot. Ah, so it's still coming same. Okay, maybe let me go a bit complex. Y, y, x, I, x, x, y, I, x, y, x, y, x, y. Right? Two. So so whatever you see in the graph is how over the number of steps, how the fidelity is changing over time, over the number of the steps. Now, the more I increase the number of the steps, the fidelity should go close to 1. So this graph, what actually shows you is how many steps you have to do those trotter slices to reach to the accuracy to a certain level so that your fidelity goes to close to 1. Yeah, you can see here. Uh, okay, I'll just zoom it. Yeah. So you can see here, my fidelity, if I go for only one trotter slice, my fidelity is close to how much? 0.126, right? Which is a very bad. That means my whatever state I have generated, it's completely, you can say completely wrong. So the more I increase the number of the steps, you see, when I'm reaching to the ninth step, I almost, so if I let's say 5 steps, 5 trotta slice, I'm getting 0.7 fidelity. That means it's getting closer to 1. So which means my simulation is giving me correct results because I'm increasing the number of the steps. Now again, I'm going again 7 to 8 to 9 to 12. Once I reach to the 12 number of steps, that means my fidelity is going to 0.9, which is close to 1. That means my simulation results are correct, almost correct, not 100% correct, but 96% correct. Now, if I go more and more and more, you see with the 46, 47, 48, my fidelity will go close to 99.9%. So this graph actually helps you to build an intuition about how many steps you have to actually go to create the accurate simulation. Since it's very difficult to show the whole circuit of that, like the whole circuit of the full unitary operator, because it's a very large circuit. Like, so yeah, when you decompose that into a single qubit gets, yeah. So this graph is actually showcasing how the fidelity is changing with different kind of trotter steps. I hope that answers your question.
Yes, sir. Thank you, sir.
Yeah. Any more questions? No more questions? Okay. Uh, yeah. So, so initially when I was preparing my slides, to be honest, I had kind of a very less idea about where exactly all of you are, like in quantum computing. So I saw some of the videos on the YouTube. Someone was explaining Grover's algorithm, and someone was also explaining some Deuce Joshua constant Vazirani. These kind of algorithms they are explaining. So I thought maybe I should explain some complicated algorithms because these people have already covered some of the basic algorithms. So that's the main intention of mine was behind showcasing this totalization algorithm, which I feel a bit hard because it's, to be honest, it's not that straightforward. In fact, I had to put also a lot of effort to understand it and to create it from scratch. So, uh, I think I should have explained some other simple algorithms also. Maybe that would create a lot of value to all of you. Anyway, but Quniverse will help you a lot if you do register. All of you just do register into the Quniverse because it's free. Nothing takes from you. So you can just register and explore. If you are interested in quantum algorithms and do quantum research, you can explore all of those algorithms, learn from it, create your own circuit, submit your jobs, and just to get into the space of quantum computing and really uh, get into a direction of a really good researcher. Yeah. So that's I would like to highlight the fact, and also uh, uh, the hospitality here I have received is really amazing. Thank all of the organizers as well as all the people who have given me this opportunity to speak in front of all of you. In fact, if I would have a little bit of more idea about mostly you are beginner, I would have created some basics stuff also. Um, so, um, so this is the first. Actually, this is the first time I am visiting in Vizag. Yeah, Srikakulam. Not Srikakulam, in Vizag itself. This is the first time I'm coming in this city. And yesterday I got a bit cold as well, some fever also. So I somehow managed to give these 2 talks, which I think to have a bit of understanding and have a uh, maybe helped you in a lot. Okay. So yeah, thank you so much for yeah attending. Yeah, thank you, thank you.
So, what do you think, guys? To me, this was such a fabulous session. It was very informative, and we must thank Mr. Tilok Sadhukan sir, who walked us through QUniverse initially in the morning session, showing us why this platform is powerful for practical quantum computing and learning. We saw how it provides a unified interface and a quantum SDK, and how it lets us run quantum algorithms on GPU processors instead of coding also, and bringing real efficiency to quantum experimentation. So, a very big thank you to Mr. Tilok sir for taking the time to guide us and for sharing such valuable insights. On a personal note, yesterday after traveling, sir actually caught some fever also. But even in that situation, he never backed off, but he took the session in the morning session, and also he have taken his time and efforts to share his knowledge to all of us in the afternoon session also. So let's give him a big round of applause for everything he has did for us. Thank you. Thank you so much, sir. So everybody, I notice most too many students have lined up for the most exciting part of today, the hackathon, the 48-hour long hackathon from multiple universities. So on behalf of the entire organizing team, I extend a very warm welcome to each and every one of you. Our esteemed faculty members and dedicated participants who valued our guests, especially those who have joined us in person mode from over 30 plus institutions and universities across all over this place. So, your presence here today truly makes this event extra special. So, a big round of applause to you all. And the most exciting hackathon is about to begin in just a few minutes. In the meanwhile, you can take rest or get some fresh air if you want to. But get ready for more knowledge blast just after the few minutes of break. Thank you, guys.
Yes, sir.
Imagine a university that discovers brilliance in the hearts of rural India, offering world. Imagine a university. Very good afternoon, everyone. We are really thrilled to kick off a 48-hour long quantum hackathon where bright minds will come together and solve real world problems using the latest advancements in quantum and showcase your talent as a platform to initiate, innovate, collaborate, and showcase your talent. And we are confident that this hackathon will lead to many exchanging and exciting breakthroughs. Before we formally begin, it's my pleasure to invite all our dignitaries, esteemed members of the statutory body, and our organizing committee members to kindly join us on the dais to inaugurate this 48-hour long quantum hackathon. I request all our dignitaries, Dr. Gnan Yala sir, Mr. Tilok sir, Mr. Srinivas Prisupati sir, our Dean of Academics, Dr. Dr. Sivaram Krishna sir, who is also the convener of this fest, and all the beloved dignitaries whoever are here. Let's welcome them with a big round of applause to inaugurate this 48-hour long grand quantum hackathon. The 48-hour long quantum hackathon is going to begin in 10 more minutes, dears. And now I'd like to request Dr. Gnan Yala sir to give you a little heads up about the quantum hackathon's guidelines and all the procedures you need to be following during the entire 48-hour duration. So I request the organizing committee to present the quantum hackathon guidelines.
Okay. So yes, a very good afternoon to everyone. So lot of guys already opened their laptops, started doing stuff. Nice, nice. Because these people so out of us four, three of them are the juries for your you know things which you have started doing till now. So I want you guys to just close those laptops and to listen to me because there are something called as guidelines. Okay, so without knowing the rules, if you go and play cricket, anyway they're gonna kick you out, right? Same probability, same rules. Ante kada. So if I wanna play cricket, I wanna play by rules. If I don't know the rules and go play cricket, anyway I'm gonna going to get, even though if hit a six, it's not a great deal. So yes, first of all, I would like to give a brief about myself for the people who did not attend the event and stuff like that. So myself, Dr. Gnandi Alla, I'm the Chief Technology Officer of DataTeach.ai, and I am a quantum research scientist from IIIT Hyderabad. So I'll be the one of the judge, I mean one of the jury for your hackathon thingy, and I am here to just present you some of the guidelines of this hackathon. Okay. So before actually going into the hackathon guidelines, which will be presented on the screen in something like 3 to 4 or 5, I mean, like in 1 to 2 minutes itself, I guess. Hey, nice. Okay. So first, I would like to say, like, I hope that you guys are in something known as a WhatsApp group, right? So about the hackathon WhatsApp group. So in that, you already have the guidelines and all, but I'm here to just give some insights from my side so that it will be added for your own protocols. Now, first things which we are gonna have is first of all a grand welcome to everyone. And yeah, initially we're gonna have general rules for the guidelines. So the general rules are the basic stuff which you guys already have an idea about. You know those basic stuff, right? You already know how it exactly be, right? Like team leader should be there, the team management should be there, you guys should maintain a code of conduct, and you guys should maintain disciplines, and yeah, you know all those rules which we'll be seeing in our colleges and daily activities and stuff like that. So these are these pretty general rules. And yeah, each team should definitely have 3 to 5 members only. Okay, 3 to 5 minimum. You can have 3 people, and maximum you can have 5 people. Got it? And that's just one of the important stuff. And team members is an important concept, and team lead is an important concept. Okay, you definitely need to have a lead for your team. There should definitely be a team lead, and we will be using him for all the point of contacts and stuff like that. So that's an important thing which to be going on. And obviously, you guys have all the stuff. So these are all normal things. And project and development rules are the things which I would like to explicitly talk about. First deal is the project which you're developing should answer some of the business problems. That's an important use case. Whatever problem you're doing, or whatever answer you're doing, or whatever code you're doing, circuit you're building, whatever stuff you're doing, should definitely answer one of the business problem. You can't come in and you can show like if you just made me a circuit and you can show like, bro, I did quantum teleportation, I will say very good, but I won't give you an award. Because what you're going to achieve by doing the quantum teleportation, what you're going to achieve by showing the E91 protocol, what you're going to do with that, you should explain that explicitly. Dude, I made E91 protocol. Why? Because I can use this compared to the classical communication stuff or classical key stuff. Why? Because that can be broken by doing this, and you can use all the stuff, whatever you wish for. Don't b- don't give me a theoretical presentation. This is not an IEEE conference. This is a hackathon which you will be providing, or you'll be building a business solution by using quantum technology. Got it? Just show me why your approach is better than the classical approach out there. Okay? And third deal is most important, documentation. There's something called as documentation. Documentation is very much important for this particular hackathon. Why? Because whatever stuff you're building, I can understand because I know quantum. Can an XYZ guy who has a company, will he be able to understand that? If I say like normally it takes n iterations, but here I'm using square root of n iterations, will he be able to understand that one? If a guy who is a stakeholder, he cannot understand that. So that's why proper documentation with all the README files, the code structure, the citations which you have used, like the arguments which you're providing. For example, let us consider you're doing a BB84 protocol. Which citation you use, which reference paper you use in order to write that one, in order to build a protocol on that, and how you're showing advantage. So all those stuff should be explained explicitly. And normally, technical guidelines, definitely Qiskit should be used. Don't use penny lane or anything because this is a Qiskit event. That's why we will be using Qiskit model. And programming language, you can use whatever stuff you want. Python, Java, and if you want to build a front end, use JavaScript or whatever you can use. That's not a deal. But definitely make use of Qiskit. And you need to make sure that you're explaining why you're using that. Okay, that's an important deal again. Now, so the main thing which I want to talk about is the how this review process actually works. So totally, there are some X number of teams which I don't want to say about, but for the final stage, 10 teams will be selected. Okay, 10 teams will be selected for the final stage, and those 10 teams should give a presentation. Okay, So that is for the second one. Like out of all the teams here, and some more people adding up. So only 10 teams will be selected, and only those teams will have the privilege to provide or to give a presentation. That too for 5 to 7 minutes. The presentation is for 5 to 7 minutes, and then the Q&As will obviously be the theoretical concept covered team. So that will be for 3 minutes. So totally you'll be having 10 minutes of time on the stage. Who? The selected 10 teams. Okay. It will be an on-stage presentation. The selected 10 teams prior to that selection, you will be having 5 reviews, 5 short reviews, no stage, nothing. So you will be sitting on your desk, you will be doing your operations, you will be doing your tasks. We juries will come to your desk at a particular allocated time being, and we will question you based on the based on the review characteristic or whatever, which will be exposed to you like half an hour to 40 minutes before that actual reviews being happened. Okay, so for example, let us consider I am doing a review one based on XYZ, and then based on that, we will be giving you marks. Okay, the marks and everything will not be that much explicitly defined, but that's the criteria, that's the selection criteria. We will be having 5 reviews in between. So if you want to get into the top 10 teams who are presenting on the stage, you should pass these 5 reviews. Okay, and we will directly say that you pass only at the only on Monday morning, I guess. Okay, so please make sure that every process which you're doing marks an important stuff. It should be an important stuff. You can't just sit here and be like, dude, I can do Sunday evening, bro. If you do like that, na, light. Okay, why? Because there will be short reviews, as I mentioned, right? So suddenly after 4 hours, we will come and we will be like, what is your progress? At that time, you should show me your progress. Like, what did you do in this first 4 hours? So you should show me that. And based on it, we will give you marks, and all these marks will be allocated. And based on the combined marks, you will be selected for the top 10. And that's how this thing works. And the reviews are divided like first 4 hours may one review, and then prior to that, next 6 hours may one more review. So like that, it will be there clearly. Anyways, you guys will be having this document so that you can revise it at the EOD, not a problem. And judging criteria and everything will be easily, they all in the document itself. That's not that much of a concern. And the main thing is the code which you're writing should not be plagiarized. That's an important concept. No plagiarism should be there. Everything should be novel. Okay. Novel architecture should be there, or novel framework should be there. If you are like, I'm doing portfolio optimization using quantum approximate algorithm, QA algorithm, I'll be doing portfolio optimization ankunda. You should not directly write the code which is in the GitHub. Do some modifications, add some toolkits, or try to increase the depth, or do whatever stuff you can. It should be a novel framework. Don't be like GitHub copy paste. No, it should be a novel framework. Okay, that's an important thing. So yeah, these are all more than enough actually. The main thing is documentation, dude. And after documentation, you need to align with the business proposal. That's an important concept. So those are the things which I would like to address here. And yeah, you can use AI, GPT, Perplexity, Claude, whatever stuff you can use, not a problem. But eventually, if you want to answer our questions when we are coming near you for the short reviews, you should be having knowledge, right? If you show me the complete output, but if you're not answering me one question, I will consider you completely use AI without your own knowledge. You will be disqualified. Simple. So that's why even if if you are using AI, get the knowledge first. And after getting the knowledge, you can obviously use AI to streamline your work or to optimize your workflow. Adavainda? Samaj gaya? Done. Purinchida? Tamil pasang Purinchida? Nice. Cool. So that's all I would like to address. Thank you so much for the time. If you're having any queries, you can ask me at this point of time. No queries? Such a smart people. Cool. Completely already. Thank you then.
Hello. How many teams are here? You don't know, right? Why did you come here? We all assembled here? Why I'm asking these questions to you is that you are in a team right now. The team may be comprising 3 to 5 people. The team lead has to communicate with his resources, with his team people, to coordinate their work and measure the progress there. The team lead, even though is an individual contributor here in the team, that guy has to coordinate what each person in the team is doing. John has covered most of the things, but some of the points which I wanted to really highlight is that whenever a problem has been given to you, for example, a protein folding, which is burning the world today, the entire research in the United States is revolving around the protein folding to come out with the drug and reduce the time of drug discovery. So that problem, apparently, I did not expect for you guys to come out with something, but it is going to be a tremendous experience for you guys because you'll be doing research on that. You'll be consulting your most important generative AI, generative tools, etc., etc. But you will not get all that information, whether you use GPT-5 or tomorrow GPT-6, whatever the research that is happening in that research. So the most important thing is that what is the problem that you are going to solve? Try to understand that problem first. So micro level, divide the problem into chunks. How the amino acids in the protein folding combine there, and the drug discovery has been expedited by understanding that particular cell is having cancerous symptoms or not. So you have to divide the story. So I'll call it as a story and divide your problem to be solved. Now, once the problem, whatever you understood, you have to articulate it. Jnana has called it as documentation. I'll call it as an articulation. You have to put in such a way that I have to understand as a judge. Your English level language should be fine. Your grammar should be fine. Right? Are you getting it? So the documentation is very important. Understand the user story or understand the problem what we are going to solve. Second thing is that when you have the problem in front of you, right? You have the coding and you have the outcome of that particular problem. Before that, there's an intermediate which is called a heart in the software development life cycle. What is that called? Nothing moves in this world without the design and architecting. Am I right? Have you heard about these terms? You are solving an industry problem now, even though you are in the fourth year or third year, whatever it is. That's why it's called hackathon. In between the story or the problem that you are going to solve, how do we basically come out and design something? This is the technology stack. This is the Java language I am using it. This is the circuit design I am doing it. This is the execution methodology that I am doing it. Please try to document that area as well, because your team members will be based on your design document and the user story or the problem statement that you are going to give to start writing the Python code. These two should form the basis for your young guys who are in the team should write the code based on that. So if the problem statement is wrong here, the code goes haywire, right? That's why a statement or a problem which is solved in the initial stages will solve $250 there. If a code is going and all, if a problem is found in the code where the problem is actually attributable to the problem there in the problem statement, then your entire team is not doing a good job there. So problem statement and your design. Second thing is that this team effort is very, very important here. Even though we called it as a review process, I use the word sprint here, right? Every problem in this world has to be boiled down to some sprints, which are achievable targets. Don't call it a review process. Call it as a sprint, because you are working in the agile way. You have got only 48 hours. Your target is 48 hours, where the sprint where the user story has to be completed in 48 hours. In 48 hours, out of 48 hours, I am going to divide your user story into chunks, which are called the sprints. If you know doctors, they do MRIs. Nothing can be found in X-rays. So what they do is, to find the exact problem, they go to magnetic resonance imaging. They got slice by slice, exactly the problem is there. Like that, when you divide your entire user story into sprint 1, sprint 2, which may be 3 hours, 4 hours. So for each of those sprints, the team lead, one person has to be nominated as designated as a team lead there. That particular person will give the task to 1, 2, 3, 4, 5 people. His job is not only to do contribution individually, but also to coordinate the activities. This is exactly what happens in the agile process in the industry. I am not a researcher, I am not a scientist, I am not a professor. I am an industry specialist. If I use protein folding, I wanted to ensure that it works in the cancer research in the Hopkins Hospital. Okay, so the design, the user story documentation, the technology stack that you are going to use. Second important thing, probably, which is a very high level thing for you, is that there is something known as the testing also. Whether it is a circuit or whether it is a Java program, we use different tools when it is a Java or a Python program, etc. In the circuit design also, IBM should be having in the Qiskit, the Qiskit framework, some technology-driven testing framework has to be there. If it is not there, IBM has to provide the testing framework for you, for the Qiskit also. That is a part of every automation framework, etc. So you have to do a little bit of testing before you come and tell myself and Trilok and other people, our product is ready. We are not going to leave if you say that your product is ready. That is a product readiness. We will assess. Where is your code? Where are your coding standards? Show me your code indentation. Execute the code in front of me, show the outcome. The last and the final, which is very important, in case of quantum computing or the quantum algorithms or the quantum Qiskit frameworks. See, tomorrow, after 5 years, one more framework will come. Frameworks are variable, right? So, but the framework will provide you all the necessary things. How do you take the libraries from that framework to design a Qiskit framework? Like, for example, there is one more case study here, which we are talking about, is the, options here. Somebody, there is one case study here, which we are talking about, quantum runaway or whatever is the quantum thing, for the swap options or for the options. Somebody should know the finance, what is an option. Even though if you go to GPT and find out, you will not have time to do what is an option. And how do I simulate a solution using AER for an option, for the portfolio optimization or whatever it is. So please try to get the business domain knowledge in the span of time that has been provided to you. So the conglomeration of your business knowledge, the user story documentation, the design and the technology stack, the IBM framework, which is a fantastic one that is available to all of us, the Qiskit, get the imported libraries from all that. And finally, what is more important is the outcome. What is the business value that you are going to give by solving this problem to the world? The next and most important thing is that how do you take this forward? Your project is left in between or something like that. How do you take this forward? What is the future outlook of this particular project or something? It is a live project. All are live projects. Whatever the case studies that have been selected by the organizing committee, full hats off to them. They have taken the industry use cases and straight away I can use this thing in an industry. If it is working fine. Little bit of customization has to be done everywhere. So outcome is very, very important. The outcome has to be corroborated with the results that are coming from a QSIT kit framework or the design what you are doing. Okay, for a protein folding, okay, this is the binding stability, right? And this is the lowest energy level that a particular molecule is attached to a ligand. So these are the things that you have to do, right? So I'm leaving it to the people, and roll up your sleeves, be comfortable. What we are looking is, we are all friendly judges at the same time. We don't want to disturb you people, right? I wanted to just touch upon certain points where when you join the industry, these are very useful. You will remember me at that time, right? Outcome is very important, which the results have to come in kind of a visualization form. No, none of your managers look at a big Excel sheet which is having 100 rows. I wanted to see a matplotlib. I wanted to see a histogram. So how can you bring that? Those, please keep it in your mind. Whatever is possible, do it. But the thing is that don't give only importance to your Python coding here. Your outcome, your results, your design is very important, right? Any questions, please call me, right? I may be here, I may not be here, but we are done, okay? Thank you very much and all the best to you guys.
Hello. I think I'm audible now. So, I'll just share some practical advices that will, I think, definitely help you to solve various kind of questions that will be available in this hackathon. So the general procedure of solving any problem, it's a not very it's a very simple way I look at it. So you have been given a problem to solve. You just try to break it down in a very small steps, right? Small couple of steps that can be achievable. So for example, you've been given a big problem that you have no idea how it works or how you can actually solve it. You have just zero knowledge about it, right? Which means you are starting or you are trying to solve that problem from completely scratch. You are a beginner just. So how, but you don't be discouraged. You can actually solve it. How you can do it? Now that's the question. We can actually break that big problem into smaller steps, and you can attain or you can do and you can achieve solve the smaller step each at a time. And by the end of it, you will be able to solve it, the big problem. Now, in the context of this today's this hackathon, I think mostly problems will be related to various kind of algorithms as well as mostly various kind of algorithms. So my suggestion to all of you, which I feel would be really, as you already have given the full access of all the AI tools, ChatGPT, Google, Sonnet, Comet, yeah, whatever the recent browsers are. So as you have got the access, so my suggestion to all of you would be like try to attack each of the problem mathematically and by step. Make your logical flow of reasoning the when you try to solve that problem, make your flow of reasoning so strong that you will have a really good understanding about what problem you are actually trying to solve. And in this way you will have the most learning experience, I would say, because it's not just only I'm saying it for the sake of saying it, but from my personal experience I have felt it numerous times. Because even around 2 years ago I was also was kind of a very beginner in quantum computing. And when I was learning it, I firstly I found it very intimidating, to be honest. Like all those equations, those Kates, bras, this and that, Hilbert space. Of course I did have a kind of an expertise in quantum mechanics, as I studied quantum mechanics rigorously. So I have that grit. But I found it initially, all looking at the circuits and stuff, I found it a bit of intimidating. But soon I try to attack the problems each at a time, and one step at a time. I got to understand about all those algorithms, and I built a basically good amount of understanding about all the algorithms. So the same thing I would suggest to all of you also, while you are trying to solve those algorithmic problems or any problems you are trying to solve in general. So just make your reasoning flow of reasoning or logical flow strong, and try to attack the problem mathematically. Not just you are just doing hadamard here, not just like that. Just try to attack the problem mathematically. How, what is exactly you want to do, how you want to do it, what are the things that you're going to get out of it, and what are the steps that you have to take for that. So in this way, I think you will develop the uh, most capabilities in terms of knowledge. Yeah. So with this, thank you.
Behalf of Rgukt Srikakulam, I would like to thank all the participants for this hackathon. And I would like to thank all the jury members for accepting our invitation. And they have a very good experts in quantum, and the problem statements are fantastic. And they have discussed a lot on the problem statements, and they have prepared 10 problem statements. And all the best and best of luck to all the participants. And let us start the hackathon. Thank you. Thank you very much.
And now it's time for the most awaited part of the entire Qiskit Fall Fest 2025 at Rgukt Srikakulam. Nothing but the 48-hour long hackathon inauguration. So all of you split up with your teams, and you guys can start your discussion. And the gigantic hackathon just started. The timer has started. You all have seen the timer, and you can start your discussions and work now. And a little heads up, guys. Please go through the problem statements document once again because a few more exciting statements might have been added. I advise all the teams to have a look at the problem statements once again. Few more exciting problem statements have been added to the problem statements. So split up with your teams, get started with your work, start brainstorming, and hope you will be as progressive as we are expecting.
హలో కనపడదు సార్ ఇక్కడ ఉండే ఎక్కడే మాట్లాడుతున్నారు స్లోగా అన్ని అరేంజ్మెంట్స్ చేస్తాము అంటే a small announcement. You can form the groups and power sockets and everything will be prepared within half an hour or 1 hour. Okay. So if you have any problem, you can ask the organizers. Okay. So you can form into the groups. We'll provide the tables and everything. Okay. Yeah. If you have any problem, you can contact the organizers. Yeah.
Guys, we're also allowing spot registration. So those who didn't register till now, you can come to the dais and you can register yourself.
Those who participant teams are going to register on the spot. The spot registration teams, the entire team need not come near the dash. Only the team lead is enough to come here, and they will give us all the details about your team. So whoever wanted to register on spot, just send your team lead here and let us get your details. To use the internet access, the Wi-Fi password is Qiskit143. All caps Qiskit 143. To utilize the internet access, the username is Qiskit. The password is all caps Qiskit143. Qiskit 143. teams who are registering on the spot, please note down your problem statement ID while you're coming to register, friend. Dear teams, to access the internet, you will find network names with TNP 001 to TNP 150. The password is also the username itself. You can use whichever the network gets connected to your devices. Okay. Yes, sir. TNP 001 నుంచి TNP 150 వరకు networks available గా ఉంటాయి. The username is same as the password. Username and password. You can connect it. You can select any random number which you are interested between 001 and 150. Dear teams, look for the network name Rgukt Srikakulam. Rgukt SKLM or Rgukt Srikakulam అనున్న network name చూసుకోండి. And the usernames are as displayed. TNP 001 to TNP 150. Password is same as the username. The teams who are participating from RGKT Srikakulam campus, I think E3 and D4 students, you have your internet access with your exam cell password and your ID number. You can use that one. All the in-person participants from other institutions, you can use the one displayed just earlier. E3 and E4 students of RGKT Srikakulam who are participating, use the internet access which you have with your exam cell password and ID numbers. And rest of the in-person participants from all the other institutions other than RGKT Srikakulam, you can use the internet access details as we have displayed earlier. And if you have any queries, one person from your team can come to the place beside the dais. Whoever want to register on the spot, dear teams, please be seated in your places itself. Our organizing team people will come to your tables and take your details. So no worries about it. Focus on your problem and focus on your learning journey. Your registration will be our responsibility. The guidelines have also been shared in the WhatsApp group for your okay. ఈ హ్యాకథాన్ వాట్సాప్ గ్రూప్లోనే గైడ్లైన్స్ కూడా షేర్ చేశారు. యూ కెన్ గో త్రూ ద గైడ్లైన్స్ ఇఫ్ యూ వాంట్ టు. Our team will be coming to your places and collect your complete data. మీ డీటెయిల్డ్ ఇన్ఫర్మేషన్ డేటా టీమ్ లీడ్స్ అండ్ ఒకవేళ మీరు ఏమైనా చేంజెస్ అయి ఉంటే ఇఫ్ ఎనీ ఆఫ్ యువర్ పార్టిసిపెంట్స్ హ్యావ్ బీన్ యాడెడ్ ఆర్ మోడిఫైడ్ our team will come to your place and collect your data. Don't worry, you need not come forward or you need not worry about it. Our team will come to your place and collect your data, guys. You can simply continue working on your problem statements. As I said, our team will be coming to your tables and collecting your data. Please have your team names fixed. Decide what your team name is, and that should not cause a potential delay, right? So, my team name fix ayi unte, when our team people come to your tables, you can give the accurate data.
ప్లే చేయనా సౌండ్ కేబుల్ దీనికి ఉండదు జాక్ సిపి మరి ఎందుకు జాక్ ఉండదు